Okay, so the most important thing is there is a test on Monday. The topics are everything up through centroids. So everything, remember, it's cumulative. So you need to be ready for old questions too. One nice thing about statics is everything pretty much builds on the previous stuff. So um, the um, the cumulative part of statics tests isn't as big a thing as in some other classes because everything you do is kind of reinforcing the old stuff. But just remember, I mean, I still might ask some questions on particle statics or whatever, vectors. Um, and the stuff that I got into last time was structures, and that is not going to be on the exam. Um, so I'd be happy to spend as much of today as you want going over questions relevant to the exam, doing problems from homework or whatever. And then when you're done with questions about that, then I'll go back to the stuff that we're working on now. Anybody want me to go over any homework questions? I just had the one problem, so I have a good guess which it would be if you want me to. It's a little complicated. Might as well do it. Yeah, let's do it. Because doing problems is fun. Everybody likes doing problems.
And the test includes like this kind of problem
Yep,
for homework aid.
that's right. You know, I mean, to be honest, on exams, I don't really usually give the hardest problems that you see in daily assignments. I usually try to keep more sort of to the middle. Um, but okay. Um, well, one thing about this problem is I don't give any thicknesses for this beam. So whenever that happens, I'm just going to assume that the thickness is negligible. So we're just going to imagine that this really is just like that jagged line, you know, for doing the geometry. Um, and so I'm going to start with a free body diagram.
Professor, when we're doing a problem like this on the test, are you also grading the FBD too?
Yeah.
Okay.
Okay. And over here on the left, we have a pin joint. So that is, I'll call that RA. That's an unknown force vector. Then the roller, the rule for that is perpendicular to the surface of contact toward the chosen body. So that's like this. And I'll call that RB. And we have the 5,000 Newton force there. And then we have the distributed load. Um, and that comes up to a maximum of 15,000 newtons per meter. And there's no weight or anything. So that's everything. And now we have to figure out the centroid of that triangle and the area of that triangle. The height is 15,000. The width is 1.5. The centroid is here. We only care about the X location of the centroid. So if I'm going from the edge side to the point side, it's 1/3 of the way. 1/3 of 1.5 is 0.5. And the area is base times height over 2. So that is 11,250. And now I'm going to redraw the free body diagram. Everything stays the same except the distributed load becomes a point force. And I'll do the table. I'll put my about point over here. So the row vector for RA is 0. The force is RAX, RAY. Cross product is 0. Then for RB, the location of that, okay, so we're going to go, so let's think about this as a right triangle. Okay, this angle is 45 degrees. That means this angle is 45 degrees. We're given that the base is 1 meter, or that, that leg is 1 meter. So you can use trigonometry, or maybe you just know for a 45-90 triangle that the height of that part is also 1 meter because of that angle. Any questions about that?
We're just assuming that the thickness of the beam is negligible?
Yes, that's right. And you're assuming that because I didn't give any thicknesses and it looks thin, so you're like, okay, that must be what I'm supposed to do, If I gave you thicknesses, you'd have to take that into account in the calculations, which would be a pain in this problem. Okay, so to get to the midpoint of that diagonal piece, we have to go from the about point 1.5 to get here, and then 0.5 to get to the midpoint. So that's 2. And then from the height of the pin to the middle of that diagonal piece, we have to go up 0.5. So this is 0.5. There's the row vector. And now the force vector. This is our coordinate system. This is a vector that is along that diagonal piece where this is 45 degrees. The way I drew that vector for RB, it's 90 degrees this way. So these are 90 degrees apart. So the angle, counterclockwise angle from the positive x-axis is 45 plus 90, so 135. You can also just do it with right triangles and think about the signs and stuff like that, but this always works too. And so the force vector is going to be RB times cosine of 135, sine of 135. Yep. So that is negative 0.707 RB, positive 0.707 RB. And so that's the force. And the cross product is I get 1.768 RB. And then the downward force of 11,250. To get to that point, we'll go from the about point over over 1.5, over another 1, and then over 0.5. So that's 2.5 plus 0.5 is 3. Since that's a vertical force, the height isn't going to matter, but I'll do it anyways. So that's just going up 1. And the force is 0, negative 11,250. And so that comes out to be negative 33,750. And then last is that 5,000 Newton force. That's at an angle 30 degrees below horizontal. So that force vector is going to be 5,000 times cosine and sine of negative 30 degrees. So that's 4,330 negative 2,500. The location of that, let's see, 1.5, 2.5, plus another 1.5 is 4. And then 1 for y. And I got negative 14,330. So Newton's second law, I guess I'm just going to write these out as equations. So add up all the x equations and all the x components and set them equal to 0. RAX minus 0.707 RB is equal to negative 4330. Then the y force components, RAY plus 0.707 RB is equal to 13,750. Yeah, that one's over, shifted over one. So that is positive 13,750. And then the moment equation, we have 1.768 RB is equal to positive 48,080. And I think that's not too hard to just solve by substitution. So RB is 27,194.6. That's a lot. And then RA for X, negative 4330 plus. So the X component, I think, is 14,896.6. And the Y component, I got negative 5,476.6. Any questions about that?
Why is this ruler slightly off? I think it was just because I kept them in trigonometry units for the first.
Yeah. Yeah, that's fine. I don't know. I mean, I always did all my calculations for like my whole career and stuff as like I always was working on big computer programs, so I'm used to just putting everything in decimals, and then just keep more digits if you want more precision. But yeah.
For checking my work,
Uh-huh.
it's easier to check my work if I go and say, oh, I did cosine of 30. And
Yeah. Yep.
I'm like, oh, that should have been cosine of 30.
Uh-huh.
It should have been cosine of 42.
32. Yeah, right. Right.
It was only off like a small amount. Those wouldn't
Yeah.
those wouldn't matter. Like
Right. It doesn't matter.
5 newtons off.
Yeah, that doesn't matter. Any other questions? Any other homework questions you want me to go over? Okay. Let's go back to the example from last time.
But I have a quick question. You're gonna be fairly like on the test, if there's gonna be like thrust in a rigid body statics
Mhm.
problem, like you're gonna say like there's thrust. on
Yes,
it.
I will.
Okay.
Yep. Um, so the example problem I started last time was this. We had a pin joint on the left and a member at 60 degrees connected to a pin joint on the right. And then these two are connected by a pin joint. And then there was a 6,000 Newton force there. All these distances were 1 meter. all these angles are 60 degrees. The masses of each of those two members are 20 kilograms. And I started with, okay, I numbered these members. So I called this member 1. That's going to be an important thing for reference. And the other one is member 2. And I call these joints A, B, and C. And for member 1, remember that I included the pins for each of those. So, so this is member 1 plus the pin at A plus the pin at B. And that's important. That changes. So what we treat the pin as being part of affects what forces act. So if I had chosen that pin at B to be part of member 2, that 6,000 Newton force wouldn't have acted on member 1. Okay, but it looks like the free body diagram here looks like this. We have RA, a weight force at the middle of 196.2, a force vector here, F12, and then a 6,000 Newton force here that is only there because I'm treating pin B as part of member 1. And the result, we got 3 equations. On 1 by 2, yep. So the first subscript is would always be what your free body diagram is of.
I just constantly am getting them.
Yeah.
Switches with her.
Right. So, I mean, that's one way to think of it is like whatever you're drawing your free body diagram of, that's your first subscript. Okay. So like if your free body diagram has a ton of these subscript notations all over, every first subscript is the thing that you're doing until you use Newton's third law and then it switches. But we'll see that on the next one. So we got RAX plus F12X is equal to negative 6,000. Equation 2 says RAY plus F12Y is equal to 196.2. And equation 3 says negative 0.866 F12X plus 0.5 F12Y is equal to 5245.05. And we can't solve these. That's 3 equations for 4 variables.
Where's the about point?
I chose my about point down here. And now we'll go to member 2. Well, we've already treated the pin at B as part of member 1, so we can't make that part of member 2. Okay? So this is going to be member 2 plus, you can think of it as the pin at B. I mean at C. Okay, so we have the weight of 196.2. Down here, we have a force vector. I'll call that RC. And now we got to be careful about the pin up here. So we're not including the pin. So all that's happening for member 2 is that it's in contact with the pin. Okay, so the only force we have here is the force on 2 by 1. We don't have that 6,000 Newton force that was acting on the pin.
F2 on 1, negative F1 on 2?
Yes. And if you don't make that switch to, like, right now we've introduced 4 new variables, right? The way it's written right now. We wouldn't be able to solve it with 4 new variables. But if you remember that Newton's third law says this is equal to negative F12, now we've only introduced 2 new variables. We've used the same F12 we did before, and now we can solve it. So that's a crucial step for this. And we'll fill out the table. For the about point, I guess I'll choose this. So I'll start with RC. Row vector is 0. Force is RCX, RCY. Cross product is 0. Then the weight force. Okay, this thing has a length of 1, and it's at an angle of 60 degrees. You could do this as 0.5 times cosine and sine of 120 degrees. And you get negative 0.25, positive 0.433 for the row vector. The force vector is 0, negative 196.2. And I think you get 49.05 there.
Why did you do a row force moment table for number 1?
I did last class, so it's in your notes from last time. And then negative F12, that is negative 0.5, positive 0.866 for the row vector.
So how did you find the y and the weight? 0.433?
I did, you can do that as, so if you think of, this is your coordinate system, and we want a vector that has a length of 0.5, and this angle is 60 degrees. Okay, so you can think of that as 180 minus 60. And so it's 0.5 times the cosine of 120, 0.5 times the sine of 120.
Another way to do it is to say it's cosine of 60, but cosine is x,
Yeah.
and x in that number is negative, so it's just negative.
Yeah. So right, you can think about it as triangles, as right triangles, or you can do it like this. I think I would recommend however you do it the same way every time, you know. I think the more you repeat one approach, the fewer mistakes you make.
Because 0.25, I thought you would use.
Oh, okay. So that's the 0.5 times cosine of 120. Yep. And then the force vector is negative F12x, negative F12y. So cross product is 0.5 F12y plus 0.866 F12x. And we get 3 new equations. So the fourth equation in our system is RCX minus F12x is equal to 0. The fifth equation says RCY minus F12y is equal to positive 196.2. And the sixth equation says, if I rearrange a little, 0.866 f12x plus 0.5 f12y is equal to negative 49.05. Okay, so now all of the boxed equations, we have 6 equations. And let's think about the variables. We have RAX, RAY, that's 2. F12X, F12Y, that's 4.
RCX, RCY?
And RCX and RCY gives us a total of 6. And with this many, it's pretty much you're just going to want to use reduced row echelon form to solve this. So we're going to have 6 rows in our augmented matrix. And 7 columns. This represents equations 1, 2, 3, 4, 5, 6. And then I'll go RAX, RAY, F12X, F12Y, RCX, RCY, and then the constants. So equation 1. RAX's, we have 1. F12X's, we have 1. Constants, we have negative 6,000. Equation 2, RAY's, we have 1. F12Y's, we have 1. And the constant is positive 196.2. Equation 3, F12X, we have minus 0.866 of those. F12Y, we have 0.5 of those. And the constant is 5245.05. And then equation 4, RCX, we have 1. F12X, we have negative 1. Equation 5, RCY, we have 1. F12Y, we have negative 1. Constant is 196.2. F12X, for equation 6, we have 0.866. F12Y, we have 0.5. Constant is negative 49.05. For the RA vector, I got negative 2943.36, negative 5,000. Anyone else get that? Yeah. Yay. F12, I got negative 3056.64 and 5196 newtons. And then for RC, I got negative 3056.64 and then 5392.2. Okay. So that's almost the answers. But when I introduced this problem last time, what I said was we want the external loads on each one of these members. Okay, so now what I really need to do is take these forces and plug them back into the free body diagrams. And anywhere, any location where we have more than one force vector, just add those up. Okay, so let's go to member 1. So we have F12 and then that horizontal 6,000 Newton force. So up here, we have a force vector of 2943.36. That's the x component of F12 plus 6,000. And then 5196. And then we have the weight force here. And then RA negative 2943.36 negative 5,000. And it's probably pretty convincing that that's that those all cancel. You get static equilibrium for those. And then member 2. So RC down here, we have negative 3056 point. 3056.64, 5392.2, a weight force here of 196.2, and up here we have negative F12, so that's positive 3056.64, negative 5196.
Get the x vector of the y of f. That's the, you have 2943.36 as the x vector for F12 on number 1, is that correct?
Yeah, so what that is if you look back at this free body diagram, we have F12 acting at that location, and we also have a horizontal force of 6,000. So it's basically, it's F12 plus the vector 6,000, 0. So that's why you get that. And so, well, what can we say about this? Basically, this is not quite in, it's almost in pure tension on one side and pure compression on the other side. The only way it deviates from that is that little bit of weight of the beams. But basically, you have a tension of, let's calculate it. So I'm going to just take the magnitude of that 2943.36. So this one is basically in a tension of about 5971. And the other one is in a compression of 60, 28. So this one's in compression of a little bit greater than this one is in tension. Okay, so that's an example of how to do this problem. And this method that I used for this works for however many members you have, anything that's statically determinate, that's solvable through statics, this method will do. I'm going to stop here for today. And then after the test on Wednesday, I'm going to give you a set of steps that you... No, the test is on Monday, and so we'll come back to this stuff on Wednesday. I mean, yeah. And let me just finish my thought for a sec. And so I'll go through a set of steps that you could go back and look and see that I sort of follow the steps. And then we'll just do a lot of example problems. We'll break up into groups, and you'll work on example problems. We're going to spend a good bit of time just getting you comfortable with this structures idea. Yep.
Are we gonna have some formulas for the same thing?
Yes. Any formula you need will be on there. The one thing I'm not planning to put on there is the loads for the joints. Okay. So like what kind of loads each joint applies, because that's something you can reason out. And I think that's something you should be able to do is look at a joint and think through like what the loads are that it applies. You don't have to do that if you want to just memorize them. That's fine too, but
Like the joint has a moment or not?
what? Yeah, that kind of stuff. Exactly. So I'm not planning to put that on the exam, but I will put centroids on of the simple shapes. And then there really aren't too many other formulas really, you know. Yes.
Will it say what shape?
Yes, there'll be a picture of the shape and everything. So I'll just copy that out of a textbook or something. Any other questions? Okay, have a good weekend.